Today's topic is Clausius Clapeyron latent heat equation. There are two Clausius Clapeyron latent heat equations. First equation, first we see the first equation, Clausius Clapeyron first latent heat equation. This is the PV diagram for a substance in liquid and gaseous state. There are two isothermal curves A, B, C, D and E, F, G, H. ABCD is isothermal curve at temperature T and EFGH is isothermal curve at temperature T plus dt. In curve ABCD, AB represent liquid state while CD represent gaseous state, and this horizontal portion BC, it represent the change of state from liquid to gas. At point B, the substance is in liquid state, and at point C, it is in gaseous state. So from point B to point C, the substance changes its state from liquid state to gaseous state. So this horizontal straight line curve BC represent the change of state of material. This occur at constant pressure P, which is known as saturated vapor pressure. When temperature is increased slightly, temperature is T plus dt, then we see the curve is similar to the curve ABCD, but now this horizontal portion is reduced, and this horizontal portion for temperature T plus dt is now Fg, which is smaller than BC. If we start from point D, then from D to C, it is gaseous state. In this state, if we move from D to C, we see that when pressure P is increased, its volume is reduced. Which is natural for a gaseous state. Pressure P is increased, its volume is reduced. From C to B, there is a change of state. Gaseous state converts into liquid state, and at point B, the material is entirely in liquid state. And then from B to A, it is in liquid state. In this state, we also see that When pressure is increased, its volume is decreased. At temperature T, we see that saturated vapor pressure is P, and at temperature T plus dt, we see that this saturated vapor pressure is increased slightly, and it now becomes P plus dP. Let V1 and V2 be specific volumes at point F and point G. Specific volumes means volume for unit mass. We consider material of unit mass, then V1 and V2 are volumes of unit mass. To prove Clausius Clapeyron first latent heat equation, we make two adiabatic curves at point F and at point G, and these two adiabatic curves are Fm and Gn. So, to prove first latent heat equation, we draw two adiabatic curves Fm and Gn from points F and G respectively, so that FGNMF, this closed curve will represent a Carnot cycle. In a Carnot cycle, there are four processes. Two are isothermal processes and two are adiabatic processes. Fg is isothermal expansion at temperature T plus dt. Gn is adiabatic expansion. Nm is isothermal compression at temperature T, and Mf is adiabatic compression. So, FGNMF is a Carnot cycle. In this Carnot cycle, we want how much heat is absorbed by the substance. In the first process, the part Fg, which represent isothermal expansion of the substance at temperature T plus dt. If L plus dL is the latent heat of vaporization at temperature T plus dt, then amount of heat absorbed in isothermal expansion Fg is Q1 equal to L plus dL. We assume that at temperature T plus dt, latent heat is L plus dL, and at temperature T, latent heat is L. Latent heat is the heat absorbed by the substance when its state changes. From F to G, we see that liquid state converts into gaseous state. At point F, substance is completely in liquid state and its state changes from F to G, and at G it is completely in gaseous state. So the heat absorbed at this process Fg will be the latent heat, and it will be the latent heat of vaporization, which we write as L plus dL, because it is at temperature T plus dT. So in the first process, which is Fg, which is isothermal expansion at temperature T plus dT, heat absorbed by the substance, we write it as Q1, and it is equal to L plus dL. In the second process, which is adiabatic expansion Gn, there is no exchange of heat because it is adiabatic process. In the third process Nm, here also state change, and the heat is now released by the substance. The amount of heat rejected in isothermal compression, we write it as Q2, and Q2 is equal to L. It is also the latent heat. Latent heat of vaporization at temperature T, we write it as L. So Q2 is heat rejected by the substance in this third process, and it is equal to L. In the fourth process MF, there is no exchange of heat because it is also adiabatic process. So in the process Fg, Q1 heat is absorbed by the substance, which is equal to L plus dL, and in the process Nm, Q2 heat is released by it, and this Q2 heat is equal to L. So now we see the net work obtained in complete cycle. In this Carnot cycle FGNMF, net work done will be equal to the area enclosed by this closed curve, and area enclosed by this Carnot cycle by this closed curve is equal to dP into V2 minus V1. If we assume this curve approximately as rectangle, then area of this rectangle will be length into breadth, and its length is Fg. Fg length is equal to V2 minus V1, and its breadth will be dP, because at point F pressure is P plus dP, and at point M pressure is P, and this difference in pressure is dP, which is the width of this rectangle. So the area of this Carnot cycle will be dP into V2 minus V1, and this is equal to the work done in complete cycle. So work done in complete cycle in Carnot cycle is equal to area FGNMF, and it is equal to dP into V2 minus V1. And for a reversible Carnot cycle, we know that Q1 upon Q2 is equal to T1 upon T2. If 1 is subtracted on both sides, we have Q1 upon Q2 minus 1 equal to T1 upon T2 minus 1, or Q1 minus Q2 upon Q2 equal to T1 minus T2 upon T2. Q1 minus Q2 is work done by Carnot engine. So we have W upon Q2 equal to T1 minus T2 upon T2, and this work done is equal to dP into V2 minus V1. So we have dP into V2 minus V1 upon Q2 equal to T1 minus T2 upon T2. Now temperature T1 is T plus dt and temperature T2 is T. Then and also we have Q2 equal to L. If we substitute all these values in this equation, we have dP into V2 minus V1 upon L. Here we substitute Q2 equal to L, latent heat, equal to T plus dt minus T. We substitute T plus dt for T1 and T for T2, and upon T, T2 is equal to T. Then this equation becomes dP upon dt equal to L upon T into V2 minus V1, which is Clausius Clapeyron first latent heat equation. To deduce Clausius Clapeyron second latent heat equation, we consider this closed cycle B, F, G, C, B. If we start from B, B, F, G, C, B. For this closed cycle, which is now not the Carnot cycle, because BF and GC are not adiabatic curves. So now this cycle is not Carnot cycle, cycle BFGCB, and the heat absorbed by the substance in this complete cycle we want to calculate first. So there are 4 processes. First process we consider is BF. In this first process, temperature of substance increases from T to T plus dt. So its temperature is increased by dt. So it absorbs some heat so that its temperature increases from T to T plus dt, and heat absorbed by the substance we write it as Q1, and it will be equal to C1 dt. C1 is specific heat. From the definition of specific heat, definition of specific heat C is given by heat dQ equal to mc dt. M is the mass. Here mass is assumed as unit because we take the volumes V1 and V2 as specific volume, that is volume of unit mass. So mass is taken as unit. Then from the definition of specific heat, which is dq equal to mc dt, put m equal to 1, we have heat q1 equal to c1 dt. We write specific heat here as c1, and it is the specific heat. C1 is the specific heat of liquid in contact with vapor. If we see this process BF at point B and at point F, material is in liquid state. So we choose C1, which is specific heat of liquid in contact with vapor. It is the specific heat of liquid in contact with vapor. At point B and at point F, material is completely in liquid state, but the transition to gaseous states is started at these points. So if C1 is the specific heat of liquid in contact with vapor, then heat absorbed in this first process is Q1 equal to C1 dt. In the second process, which is Fg, now heat absorbed will be equal to latent heat of vaporization as in previous case, and it is equal to L plus dl. Now the state change from liquid to gas, and heat absorbed will be latent heat of vaporization, and at temperature T plus dt we assume is as L plus dl. So in the process Fg, in the second process Fg, heat absorbed Q2 will be L plus dl. In a similar manner, we can find the heat in third and fourth processes. In third and fourth process, heat is not absorbed, but in these two cases heat is rejected by the substance, and these heat rejected by the substance in third process we write it as Q3, and it will be equal to C2 dt in a similar case as Q1 equal to C1 dt. Now in Q3 equal to C2 dt, C2 is specific heat of gas, because in this third process, which is GC, third process is GC, and at point G and at point C the substance is in gaseous state. So if C2 is specific heat of gas in contact with liquid, then heat rejected by the substance in this third process GC will be equal to Q3 equal to C2 dt, and similarly in last process part CB, the heat rejected by the substance Q4 will be equal to latent heat L. Net heat absorbed in this complete cycle will be Q equal to Q1 plus Q2 minus Q3 minus Q4. Q1 and Q2 are taken as positive, because these are the heat absorbed by the substance, and Q3 and Q4 are taken as negative, because these are the heat rejected by the substance. So net heat absorbed Q equal to Q1 plus Q2 minus Q3 minus Q4. Substitute all the values of Q1, Q2, Q3 and Q4. Q1 equal to C1 dt, Q2 equal to L plus dl, Q3 equal to C2 dt and Q4 equal to L. We have the heat absorbed Q equal to C1 minus C2 into dt plus dl. C1 dt minus C2 dt. In these two terms, we take dt as common, so that we have C1 minus C2 into dt plus dl. Net work obtained in the complete cycle, net work done W will be equal to area of the cycle BFGCB, and this work done and this area will be dP into V2 minus V1 as in previous case. Now from Clausius Clapeyron first latent heat equation, which was dP upon dt equal to L upon T into V2 minus V1, we take V2 minus V1 to left hand side, so that dP into V2 minus V1 equal to L upon T dt. And dP into V2 minus V1, which is work done, it will be equal to the net heat absorbed by the substance. So L upon T dt, which is equal to work done, and which is equal to Q, the net heat absorbed by the substance. So this equation now reduces to this: L upon T dt equal to Q. dP into V2 minus V1 is equal to W, and W equal to Q, and Q is C1 minus C2 dt plus dl. So L upon T dt equal to C1 minus C2 into dt plus dl. Dividing by dt, we have dl upon dt minus L upon T equal to C2 minus C1. And this is the Clausius Clapeyron second latent heat equation. As latent heat decreases with increase in boiling point, in this relation, in expression dl upon dt, T is boiling point. At boiling point, liquid state converts into gaseous state. So T is boiling point, and L latent heat decreases with increase in boiling point. So L decreases when T increases. So dl upon dt is negative. So left hand side is negative. So we must have right hand side equal to negative quantity. So C1 must be greater than C2. C2 must be less than C1. From this equation, which is Clausius Clapeyron first latent heat equation, dP upon dt equal to L upon T into V2 minus V1, we can find out the effect of pressure P on boiling point and on melting point. When substance goes from solid to liquid state, it will be at melting point, and when substance goes from liquid to gaseous state, it will be at boiling point. So in this relation, T is either melting point or boiling point when state of material is changed from solid to liquid or liquid to gas. When a liquid converts into gas, we know that volume always increases. Volume of the gaseous state is always greater than volume of the liquid state. So in right hand side, V2 will be greater than V1. When liquid converts into gas, V2 is greater than V1. Volume always increases. V2 is greater than V1. So right hand side will be a positive quantity. So left hand side will also be a positive quantity. It means dP upon dt must be positive. It means when P increases, T must also increases. So when pressure increases, boiling point also increase. P increases, then T increases, and T is boiling point. This is the case for effect of pressure on boiling point. Now for melting point, when solid converts into liquid, generally for most of the materials volume increases. In this case also V2 is greater than V1, right hand side is positive, and dP upon dt is positive, and it means that when P increases, T must also increase. So most of the materials for which volume is increased when material substance change from liquid state, from solid state to liquid state, when their volume is increased, then with increase in pressure, its melting point T also increases. But in some cases, like ice, when ice melt and convert into water, liquid state, its volume decreases. So for the case of ice, V2 is less than V1 and right hand side is negative. So left hand side will also be negative. So dP upon dt is negative. It means that if pressure P increases, T is decreases. That means melting point for ice decreases with increase in pressure. So this first Clausius Clapeyron latent heat equation is useful to find the effect of pressure on melting point and boiling point.